Chapter 12. A famous theorem. The most famous thing about Pythagoras is not his order at Croton, nor the weird legend of his spending years in a cave and gaining magical powers. It is simply a theorem or formal rule of geometry. The Pythagorean theorem says, in any right-angled triangle, the sum of the squares of the two sides is equal to the square of the hypotenuse. This theorem and its proof were a key advance. It became a cornerstone of ancient geometry and had more influence on theory and more practical applications than any other. Later writers would call it the measure of gold, but perhaps Pythagoras ought to be most famous for something else. He was the first to teach mathematics as part of a broad education. The origin of mathematics. The term mathematics originated from Pythagoras' course. Pythagoras gave lectures on mathemata. In the language of his time, that was the word for studies, but his use of it came to mean mathematics. Pythagorean mathemata covered a very large field, but all the parts were interrelated. It was a curious fourfold range of subjects: music to elevate the soul, numbers and their properties, ancient Babylonia lore about the planets, and abstract rules of the new theoretical geometry. Each topic was studied from the mathematical standpoint, and the whole course constituted the initiation into the secret order. The term mathematician meant one who was admitted to the inner mysteries, as distinct from a hearer or beginner. Mathematicians had to follow a rigorous course for several years, with a stern daily program of meditation, exercise, and study before they were even permitted to hear Pythagoras intone some teachings behind a curtain. Only after full initiation could they attend his actual lectures. The proof of the Pythagorean theorem. Pythagoras may have begun by announcing to his students, "I have found at last the solution to a problem that has long been puzzling us." A hush of awe fell on the gathering as Pythagoras, in white robe and gold sandals, his head crowned with a golden wreath, took pointer and string and straightedge and began to lecture. Here is the Egyptian right-angled triangle, the one used by the rope stretchers, where the sides of the right angle are 3 units and 4 units, and the hypotenuse is 5 units. He drew it on a sandy space and then added a square on each side and inner squares. There, you can see. By counting or by calculating the square units, that the total area of the squares on the 2 sides of the right angle is equal to the area of the square on the hypotenuse. He beckoned to the newcomers, who crowded close, multiplying and counting at the same time. 3 times 3 plus 4 times 4 equal 5 times 5. 9 plus 16 equals 25, until all their heads nodded in agreement. Now, let me show you a Greek design involving right-angled triangles. He drew their attention to the tiled floor on which they were standing, and then traced a similar pattern on the sand, outlining the important parts. Here, the 2 sides of the right angle are equal, and the same relation holds. With his pointer, he indicated one triangle and the related squares, and they all counted together. Look, 2 triangles plus 2 triangles equal 4 triangles. The total area of the squares on the 2 sides of this right-angled triangle is likewise equal to the area of the square on its hypotenuse. Again, he waited until the newcomers nodded their assent, and then continued. In India, the priests know other constructions that give similar results. They guard these numbers closely, but we have found some of them. In Babylon, a priestly astrologer whispered to me that there was a secret about this mystery that had never been penetrated. Now the attention was almost breathless as Pythagoras intoned solemnly, "That secret is our problem." Would the same relation always be true of any right-angled triangle, no matter what the length of its sides? And how could you show this? At this dramatic moment, he withdrew behind a curtain, while attendants played on stringed instruments to indicate an intermission. Pandemonium broke out among the assembled initiates. All the newcomers began talking at once, making suggestions, arguing and shouting. The older mathematicians, who had worked on the problem themselves, were less noisy, but even more excited. Finally, Pythagoras reappeared. Silence instantly fell over the group as he resumed his lecture. I will now show you how to construct a wondrous figure which discloses that the answer is always yes. The older ones amongst you will realize that by slowly and carefully defining each step of the construction and using a few simple theorems that you already know, this demonstration can be made into a rigorous proof. Today, I will just draw it quickly so you can all see my great discovery. He signaled to the attendants to smooth the sand and began to draw, using his pointer to emphasize his words. Watch this beautiful construction. I make a square frame, any size, and in its corner I place a small square, any size. Next, I draw straight lines, continuing the sides of the small square to the edge of the frame. Do you see what my frame now contains? A smaller square and a medium square, and 2 equal rectangles. And next, we are almost there. I simply add diagonal lines across the rectangles. This is the figure I need. My frame now contains a small square, a medium square, and 4 equal right-angled triangles. Now I will ask you to look more closely at this figure. Pythagoras beckoned to the attendants, who poured colored sand from jars onto the parts of the drawing so the pattern showed plainly. Look again. He used his pointer and spoke with care. All the triangles you know are equal. Each is the same triangle in a different position. Now notice how the triangles touch the squares, especially triangle 2. You can see that the small square is the square on the short side of the triangle, and the medium square is the square on the long side of the triangle. So my frame is completely filled by 4 equal right-angled triangles, plus the square on the short side and the square on the long side. Pythagoras paused, while a low murmur of awe arose from the initiates. Now watch, he intoned. And while they all craned their necks to see, and the attendants poured more colored sand, Pythagoras drew his final masterful figure. Watch well. I have only to swing and push these 4 triangles around like this, so that they fit perfectly into the 4 corners of the frame. And my frame is now completely filled by the same 4 equal right-angled triangles plus the square on the hypotenuse. Therefore, in any right-angled triangle, the area of the square on one side plus the area of the square on the other side will add up to the area of the square on the hypotenuse. A mighty shout, we can imagine, went up from the assembled inner group of the secret order, for this theorem was a true landmark in the development of geometry by the Pythagoreans. Almost all later geometric work involving lengths and measurements was based upon it, and this style of solving problems, especially equations, by diagramming them, would remain a chief trait of Greek geometry. But to the initiates who first heard it, the theorem seemed like a mystical revelation. Tradition says that Pythagoras himself celebrated the occasion by a noble sacrifice, an ox or 100 oxen, to his divine father, Apollo. Some ancient writers dispute this, as the Pythagoreans were vegetarians. Whatever the offering, we can easily picture the festivities described in the verse of legend. Doubtless, the mathematicians chanted, torches waved, and smoke rose from the sacrificial altar, the day Pythagoras, the famous figure, found, for which he brought the gods a sacrifice renowned.